Seeing disease in three dimensions, why time, space, and frequency matter. Number 1519, BPT 076, January 31, 2026. Gerald C. EclaireMD Foundation. Category: Research Methodology. Preface: Over the past 17 years, I have read approximately 10,000 medical papers. I did not read them to follow academic fashion or to accumulate citations, but to answer a simple and practical question: how do chronic diseases such as obesity and type 2 diabetes, and their induced mortality diseases such as cardiovascular disease, chronic kidney disease, stroke, and dementia, actually develop, progress, reverse, become permanent, and ultimately fail inside a real human body? After reading so many studies, one conclusion became unavoidable. Very few medical papers truly examine disease as a continuous process with clear cause and effect. Most medical research relies on statistical group comparisons over short time windows, which are still snapshots. Even studies labeled as longitudinal often compare only to time points, such as baseline versus endpoint. From a systems perspective, this remains snapshot thinking. Human disease does not behave like a snapshot. It behaves like a movie. My research results are not static observations. They are dynamic trajectories evolving over time. Three-domain view of disease. My research approach is different. I do not view disease through a single lens. I analyze disease simultaneously through three domains: time, space, and frequency. Even viscoplastic energy models and topological patterns inherently contain both time and space domains. This three-domain framework is common in mathematics, physics, and engineering, but it remains rare in medicine. These ideas did not begin as theory. They came from real human data. My longitudinal dataset. Over the past 17 years, I have collected dense and continuous data from my own body. This dataset contains over 4 million data points across hundreds of categories, including glucose, blood pressure, body weight, visceral fat, lipids, sleep, exercise, food intake, and many other lifestyle and physiological variables related to metabolic conditions and their induced mortality diseases. This is not a collection of clinic visits from many patients. It is a continuous record spanning more than 6,000 days of my own health history, compared with conventional medical datasets. It is a movie rather than a still photograph. Viscoplasticity and topology, space, and time. Together, viscoplasty is built on the stress-strain space, which is a spatial relationship. Stress and strain define the state of the system at any moment. That is the space domain. The cumulative energy curve derived from stress-strain behavior represents the time domain. Topology is built on a configuration space. Instead of stress and strain, it describes the relative positions, connectivity, and geometric shape of system variables. At any moment, the system occupies a position in this space, which defines its structural state. In both frameworks, space defines the instantaneous system state. Time enters when the system moves through that space. In viscoplasticity, time governs how stress produces strain, how damage accumulates, and why deformation becomes irreversible. In topology, time governs how system shape and connectivity evolve, revealing structural transitions. In short, viscoplasticity and topology both integrate space and time. Space defines state. Time defines trajectory. History defines outcome. This is why both frameworks are well suited for modeling chronic conditions and mortality diseases as dynamic and often irreversible processes. VMT NTDA complementary Rawlison. My paper on obesity and type 2 diabetes versus diet and walking opening parenthesis No.1518. I applied to complementary models, the viscoplastic medicine theory VMT model, and the topologica all data analysis TDA model. The VMT model is designed to quantify accumulated damage. In VMT, I define an output strain, such as BMI or average glucose, and examine how multiple input stressors, such as diet and exercise, contribute energy to that strain. These stressors include food portion size, carbohydrate and sugar intake, and walking steps. The core of VMT lies in the strain-stress space domain, where each stressor contributes a measurable energy area. From this space domain calculation, I derive each stressor's VMT energy contribution ratio. VMT also operates in the time domain. By integrating energy contributions year by year, I construct a cumulative energy curve. This curve reveals when damage accelerates, when intervention becomes effective, and when the system pivots from deterioration towards stabilization or reversal. In short, DMT answers how much cumulative stress the system has absorbed and when that energy translates into disease expression. TDA shifts attention in a different way. Instead of focusing on energy magnitude, TDA focuses on movement and shape in space as time unfolds. It tracks how strain and stress coordinates move through multidimensional space, emphasizing clustering, divergence, convergence, and outlier emergence. TDA captures transitions that may not yet produce large cumulative energy but signal approaching structural instability. In TDA, a hole or a bridge in the data can represent a period of metabolic crisis or a transition into a new disease state, such as my 2025 stroke event. This approach treats health as a manifold, a shape that can bend, deform, or break, rather than as a flat line or single trajectory. My analysis of the hemorrhagic stroke on June 21, 2025 serves as a clear postmortem of a complex system failure. I identified the low-frequency root cause, nearly 20 years of cerebral microvascular calcification, together with the high-frequency trigger, an acute blood pressure spike to 175 mmHg. This is exactly how engineers analyze bridge collapses or machine failures, by separating long-term structural degradation from the immediate triggering event. In contrast, clinical stroke analysis often focuses only on the trigger, while overlooking the accumulated structural damage that made the failure inevitable. I have recognized that biology already behaves like a structure under load. Just with different materials and timescales, chronic stress becomes fatigue, compensation becomes plastic deformation, stroke becomes rupture after long-term weakening plus a trigger. The radar chart used in TDA is a pure space domain visualization. It represents multiple stressors or biomarkers at selected time instants, when multiple radar charts are superimposed or compared. Spatial shapes and distances reveal how system geometry evolves across time. The chart itself is spatial, but interpretation becomes temporal. Together, VMT and TDA provide complementary insights. VMT quantifies cumulative damage. TDA detects early structural shifts. One measures how much damage has occurred. The other shows how the system is reorganizing itself. Topology has been widely used in medical imaging because of its geometric nature. My work extends topology to fluid state pathophysiology and physiology, where variables continuously evolve rather than remain fixed. Frequency domain, the missing dimension in time and space. I also rely heavily on the frequency domain of signal processing discipline, which is largely ignored in conventional medical research. Different biomarkers operate at different natural frequencies. This is not noise, it is structure. Blood pressure is a high-frequency signal. It fluctuates minute to minute and often responds first to emotional stress and vascular stiffness. Glucose operates at a medium frequency. It responds meal to meal and to changes in physical activity, reflecting metabolic control and insulin resistance. Body weight and visceral fat are low-frequency signals. They change slowly over days, weeks, months, and years, representing accumulated structural change. This is why obesity control requires a longer time period than glucose control. In my paper No.1518, the pivoting year for obesity occurs later than that for type 2 diabetes. This frequency hierarchy is critical for cause-effect reasoning. High-frequency instability appears first. Medium-frequency dysregulation follows, and low-frequency deterioration reflects long-term damage. By analyzing biomarkers from high frequency to low frequency, such as blood pressure before glucose and glucose before weight, I can infer sequence, causality, and approximate timing. My observation that obesity pivots later than type 2 diabetes is a critical finding. It suggests a hysteresis effect. The body's structural weight responds more slowly to intervention than its metabolic glucose state. Using this approach, I have also identified that my recent hemorrhagic stroke was primarily caused by long-term cerebral microvascular calcification originating from uncontrolled diabetes during 1991 to 2010. An acute blood pressure spike to 175 mmHg served as the immediate trigger on June 21, 2025. In finance, this approach is called technical analysis. In engineering, it is called signal processing. In medicine, it is the key to causality. Prediction and limitations of conventional research. Using my 17-year dataset together with VMT and TDA, I can estimate which major mortality disease is most likely to occur and within what approximate time frame. These conclusions are not speculative. They are based on temporal ordering, spatial movement, frequency sequencing, cumulative energy analysis, and repeated validation. This is not fortune-telling. It is science-based prediction grounded in system behavior and long-term data. Most medical papers cannot be read this way because the data is insufficient. Time resolution is sparse. Spatial relationships are reduced to isolated variables. Frequency. Information is averaged away. Variability is treated as noise instead of signal. This does not mean statistics is useless. It is an important tool for population guidelines, but when used alone, it collapses time, space, and frequency into a single number. Chronic disease and death are not numbers. They are processes. Once disease is viewed as a moving system evolving across time, space, and frequency, many accepted conclusions feel incomplete, and many unanswered questions become obvious. Conclusion: the viewpoints presented in this article are not philosophical opinions. They are conclusions drawn from long-term data, systems reasoning, and first-principle analysis. After studying disease behavior across time, space, and frequency domains, I am confident this framework reflects biological reality more accurately than snapshot-based statistical approaches. Chronic diseases such as obesity and type 2 diabetes do not emerge suddenly. They evolve through long-term stress accumulation, compensation, loss of reserve, and eventual failure. Treating disease as a static state measured at isolated time points obscures this process. Trajectory-based view is necessary. The human body is one of the most complex systems known. Relying solely on linear statistics limits our ability to protect health and prevent disease. Space domain analysis reveals that biomarkers are coupled and interactive, not independent. Ignoring these relationships leads to incomplete conclusions. The frequency domain adds critical causal insight. High-frequency signals respond first. Medium-frequency signals follow, and low-frequency variables reflect accumulated damage. This hierarchy allows inference of sequence, causality, and timing. Within this framework, VMT and TDA serve complementary roles. VMT quantifies cumulative damage. TDA detects early structural instability. Together, they provide both magnitude and early warning perspectives. Based on 17 years of dense longitudinal data and repeated validation, this integrated approach allows estimation of likely mortality, disease categories, and approximate time frames. The difficulty in recognizing such findings in conventional literature reflects limitations of tools and incentives, not lack of rigor. In summary, disease should be understood as a moving system, not a snapshot. A three-domain framework incorporating time, space, and frequency provides a clearer, more predictive, and more biologically faithful understanding of chronic and mortality disease progression. This approach does not replace statistics. It goes beyond it, toward a deeper and more actionable science of health and disease. I believe this work can help bridge physiology and control theory, and if digitized into a wearable AI system, it could move medicine from a reactive model that treats the fire after it starts to a predictive and preventive model that monitors heat accumulation in the wires before the fire occurs. Disclaimer: I write this paper not for fame, but to share what I have learned so others can understand health, prevent disease, and live longer, healthier lives. This content is provided for educational reference only and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered or republished as your own. All intellectual property rights belong to the author, Gerald C. HSU. This content is provided for educational reference only and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C.